Today's daily LeetCode problem of the day is regions cut by slashes, number 959. For this problem, we're given an n by n grid, which is composed of 1 by 1 squares, where each 1 by 1 square consists of a slash, backslash, or a blank space. These characters divide the squares into contiguous regions. We're given the grid represented as a string array, and we want to return the number of regions, and we want to note that a backslash character is alone, but it's represented by 2 backslashes because it's escaped. So, for example 1, as you can see here, our input is space, slash, and then slash space. So this is our space 1 by 1, and then this is our slash 1 by 1, and then another slash 1 by 1, and another space 1 by 1, ultimately dividing this grid into 2 separate chunks. Example 2, we only have 1 slash, so all this white space is still connected. Example 3, we have 1, 2, 3, 4, 5 separate spaces, while the slashes make kind of a diamond shape. So the topics for this question are array, hash table, depth first search, breadth first search, union find, and a matrix. So for this problem, it is a very difficult medium problem, but we are going to address it by considering each square as 4 regions in itself. This is because if we have our square, this is 1 1 by 1, 2 1 by 1s, 3 1 by 1s, and our 4th 1 by 1. So if we have example 1 here, where we have a slash here and a slash here, that divides this grid into 2 separate sections. However, we can also look at it as the grid itself could have 4 sections. So each grid has the ability to be cut in a cross shape, like so. Or each 1 by 1 has the ability to be cut in a cross shape like so. So while we're looking at these squares, we need to consider what parts of the squares are going to be connected. We can look at this as like 1, 2, 3, 4, 5, 6, 7, so on and so forth. So each of these are going to be separate little chunks of our squares. When we have a slash like this red slash in the top right, this is separating chunks 8 and 5 from 6 and 7. So 6 and 7 are connected, 8 and 5 are connected. However, there's no way for 8 to be connected to 7 as it's been separated. 7's connected to all these squares, this square, but because the slash down here is separating it from any of the other nodes that are connected to 8, 7 and 6 must be in a separate region. So we can consider this square at each of our 1 by 1s by starting with 4 regions, and after we either implement a space, which is going to get rid of any separators, a slash, which is going to separate them, or a backslash, which is going to separate them, we can look at all 4 regions as disconnected until we further analyze them. So our goal is to determine the total number of distinct regions formed within a grid. And there's 3 or 4 approaches. We can either expand the grid and kind of draw our slashes in with 1s, 0s and 1s, 1s representing slashes, 0s representing empty space. We can also take a disjoint set union, where we would address each of those sub-regions in a square as triangles, or we can take the approach of a disjoint set union graph. So with the graph, we are going to address each corner as a node. So we can look at an example of if we have a slash and then backslash and then backslash and then slash, creating like this diamond shape, we can consider the slashes as connectors rather than dividers, turning this average grid into a graph with 9 edges. These edges being 0, 1, 2, 3, 4, 5, 6, 7, 8. And our slashes are connecting these edges. And we want to track which edges the slashes connect. So in this situation, our first slash connects 1 to 3. Our backslash connects 1 to 5. Our backslash connects 3 to 7. Our slash connects 5 to 7. So it creates a full loop, meaning there must be at least one region here and regions outside of this area as well. So we are going to consider a slash as something that connects the top right point of a cell to the bottom left point of a cell. We'll consider a backslash as a connector from the top left point of a cell to a bottom right point of a cell. And we are going to consider an empty space as not adding a new connection. So our edges of our grid are going to form the boundaries of a graph, creating an initial region. As we connect the slashes, cycles may form, indicating the creation of new regions within the graph. By tracking the total number of cycles formed while iterating over our slashes, we can determine the final count of the regions. So we're going to manage our connected components using a disjoint set union data structure. And we will start by connecting the boundary points as the first regions. As we process the rest of the cell, we will treat each slash as an edge and a union to the corresponding vertices. If a union operation reveals that the vertex already shares the same parent, it's going to indicate a cycle, prompting us to increment our counter. So we're going to initialize a parent node, and we're going to treat it kind of like a tree. So we're going to go from one node to the next node to the next node. And if we can get back to the parent node from that node, we have a cycle. So we're going to first initiate a couple variables, our grid size, our points per side, and our total points. We're then going to create a parent array to represent our disjoint set. And then we're going to loop over each point and set its parent to 0. So our parent of 0 is going to be our top left corner, and we want to make it the root of all of the other points. And then we can iterate through each cell in our grid and decide if it's a forward slash or if it's a backslash, and we can calculate the indices that it's going to connect. We'll then have a helper function find, and that find function will find the parameters of the parent array. Ultimately, our helper function is going to define a union between nodes. So let's go ahead and start coding this. First thing we need to do is identify our grid size, our points per side, and our total points. So we're going to have an integer grid s, and that's equal to our grid dot length. We'll then have our integer point per side, and that's equal to our grid size plus 1. So that's how many points we're going to have per side in our grid, and then we're going to initialize our total points. So int total points will be equal to points per side times points per side. So basically, points per side squared is going to be the total amount of points that we're going to have within our grid. So let's say, for example, we have a 3x3 grid. Grid.length is going to be 3, so grid size is going to be 3. So 3 plus 1 is 4. So the total points that we're going to have in that grid is 16. It's easier to do it with the 2x2, so we can see it on like example 1 grid. So if grid length is 2, 2 plus 1 is 3, points per side is 3 times 3, so 9. So like we showed before, 0, 1, 2, 3, 4, 5, 6, 7, 8. That would be the total 9 points that we have in our grid. We'll then initialize an integer array called the parent array. So we're going to keep track of all the parent nodes in our disjoint set. So we're going to have an integer array parent. That's going to be equal to a new int of total points. We're going to keep track of the parent of each point. So then we're going to have arrays.fill our parent array with -1s because we are not setting any of their parents as of yet. We'll then connect all of our border points, all the points on the edge, to each other. So for int I is equal to 0, as long as I is less than points per side, I plus plus. Same thing for j, int j is equal to 0. Sorry guys, I have a huge migraine. As long as j is less than points per side, j plus plus. And then we're going to check if either I is equal to 0. So these are our cases if a point is on the edge of the grid. So if I is equal to 0, or j is equal to 0, or I is equal to points per side -1, or j is equal to points per side -1. So those are the 4 cases where a point will be the edge on the edge of our grid. So if any of those are true, we're going to have integer point be equal to I times our points per side plus j, and then our parent of point will be equal to 0. So all this is basically doing is identifying which point we are looking at using our I and our j. So it's either going to be our 0, 1, 2, 3, 5, 6, 7, or 8. And then we're going to associate node 0, or our top left corner, as the parent to all those, because node 0 can connect to all of those points without any slashes or backslashes. We are then going to set our root node, or node 0, to -1. So it can't be its own parent. So we're setting it to have no parent. So parent of 0 will be equal to -1. And then we can identify our region count. So int region count is equal to 1. Basically, we are deciding that because we have identified this region where all the corners connect back to our root node, we have at least one region identified. We are then going to process each cell in the grid to see if there are more regions we can identify. So we're going to have another nested loop for int I is equal to 0 as long as I is less than our grid size. So I plus plus, or int j is equal to 0 as long as j is less than our grid size, j plus plus. So we're going to treat each of our slashes as an edge connecting 2 points. So in this case scenario with top right slash, that is connecting to node 2, the top right corner, to node 4, the middle point. So how are we going to process this? First, we're going to have an if our grid of I dot char at j is equal to slash. Then we are going to have an integer top right equal to I times our points per side plus j plus 1. So grid of I, grid is a string array. So we're looking at whatever string we're currently on, which is what I is incrementing through. and then we're looking at character at j. So it's first going to look at empty space, and then it's going to look at our slash. When it sees our slash, it is going to enter in to this if statement. So it's going to identify the top right as I. So I is currently 0 times point per side. Points per side is going to be currently 3. So 0 times 3 is 0 plus j plus 1. So if we're looking at the empty space, it's going to be 0 plus 1, so 1. So top right is going to be equal to 1, 0, 1. So that's going to be our middle value. When we look, which is correct, 0, 1, our middle value connecting down here, there is no slash. Then when we look at the slash part right here, anyways, if we look at the slash, we're still I is equal to 0 times point per side, which would be 3. So 0 plus j is going to be equal to 1. 1 plus 1 is 2. 0, 1, 2. That is our top right corner we're supposed to be looking at. We're then going to have int bottom left is going to be equal to I plus 1 times points per side plus j. So that is going to identify our bottom left point that our top right point is going to be connecting to. Now all we have to do is we are going to update a region count by calling to a helper function. So our region count is going to plus equal our union of our parent, of our top right, and our bottom left. So we're going to see if this union in our parent array from our top right to our bottom left node creates a new region. If it does, we'll return 1. Otherwise, we'll update it, return 1. Otherwise, we're not going to update it, and it'll stay the same. Else, if our grid of I dot char at j is equal to backslash. Remember, we have to do 2 because it's escaped. Our int top left will be equal to I times point per side plus our j. And then our int bottom right will be equal to I plus 1 times point per side plus j plus 1. So that's going to identify our top left and our bottom right when we come across a backslash. And then we're going to call to our union function again. So our region count will plus equal our union of parent, top left, and bottom right. After we break through these loops, we should be able to return our region count. So let's go identify this helper function. So this helper function is going to find the parent of our set, and it's going to identify the connections between two nodes and see if there is a new region because of it. So we have our private, it's going to return an integer union. It's going to receive our integer array parent, an integer node 1. We could call it A, and then int B. Those are our nodes A and B. So we're going to have an integer parent 1, which is going to be equal to find parent and A. And we're going to have an int parent 2, which is going to be equal to find parent and B. So find is going to be another helper function, and it's going to find the parent of A, and it's going to find the parent of B, so we can compare the parents to see If the parent is equal to one another, that means that we have created a new region. So because, let's say if we have this slash and this slash, both have the same parent setting back all the way to 0. So this is a full connected region. So let's go ahead and identify our find function. So we're gonna have a private int find, which is going to receive an integer array parent and an integer node. So if our parent of node is equal to -1, we're going to return our node. Otherwise, we're going to return our parent of node is equal to the find parent and our parent of node. Basically, we're going to recursively look for the parent of this node until we get back to -1, which is our node 0, which doesn't have a parent. So we're going to recursively look until we find its node. If it has the same parent, it will return node. So now we're going to check if parent 1 is equal to parent 2, we can return 1. So the nodes already are in the same set, a new region is formed. Otherwise, we're going to have parent of parent 2 is equal to parent 1. So we're going to unionize the set. We're going to basically make it official, and we can return 0. So no new regions were formed in this case scenario. So if we run this, passes our test cases, and if we submit it, passes all solutions. Let's do it in Python. Python is basically the same thing, very similar. We're gonna have our grid size is equal to length of grid. We're gonna have our points per side are equal to our grid size plus 1. Our total points are equal to points per side times points per side. Then we're going to have our parent array, which is going to be equal to -1 times the length total points. Then we're going to go for I in range points per side, for j in range points per side. If I is equal to 0, or j is equal to 0, or I is equal to points per side minus 1, or j is equal to points per side minus 1. Then we're going to do point is equal to I times points per side plus j. And then our parent of point is going to be equal to 0. Again, this is initializing all of our edges. This is going to connect all the edge points. We're then going to set the parent of the top left node to be -1. So parent of 0 will be equal to -1. And then we're going to initialize our region count to 1. So for I in range grid size, and for j in range grid size, we're now going to treat each slash as the edge connecting 2 points together. So if our grid of I of j is equal to a slash, we're going to set its top right equal to I times points per side plus j plus 1, and then the bottom left will be equal to I plus 1 times points per side plus j. And then we can update our region count. So region count will plus equal self.union of our parent array, our top right, and our bottom left. Now we could do the backslash, so if grid of I of j is equal to backslash, then our top left will be equal to I times points per side plus j. Our bottom right will be equal to I plus 1 times points per side plus j plus 1. And then we'll update our region count again. So region count will plus equal self.union of parent, top left, and bottom right. And then we can return our region count. Now let's go ahead and define these two functions. We're going to have our union function and the define function. So define union, it's going to have self, parent, node A and node B. And so parent 1 is equal to self dot find parent of A, and parent 2 is equal to self dot find of parent and B. We'll then have if parent 1 is equal to parent 2, return 1. Otherwise, our parent of parent 2 will be equal to parent 1. Return 0. So let's define our find function. So def find self, parent, and node. And for this function, if parent of node is equal to -1, so it connects back to our 0 node, then we can return our node. Else, if our parent of node is equal to our self dot find parent and parent of node, then we can return our parent of node. So if we run this, passes our test cases, and if we submit it, passes all solutions with a time complexity of O of n squared. So thank you, and follow for more daily LeetCode solutions.